that I gave. Okay, this is a talk about edge turbulence in magnetic fusion plasmas, which I gave at the American Physical Society meeting in Philadelphia, April 3rd. It's a 10-minute talk, and we're recording it for Joe. And David is running the recording, and maybe he'll talk at the end, and maybe we'll get to Kevin to talk. Okay, so I'll go through this almost like I did at the meeting. This is a talk about magnetic fusion plasma turbulence. The co-authors are me, Klaus Halacek from Germany. What?
Should I zoom in?
Yeah, zoom in. Can you see that now? Klaus Halacek from Germany. John Lorenz from Princeton Scientific Instruments, company that made the camera. Ricardo Makeda, Darren Stotler, and Jim Terry from UTL and MIT. Next. Okay, so here's the picture of the NSTX plasma. It's kind of a ball. That's the sketch of it. And the magnetic field contains the plasma. The magnetic field line, the direction, is indicated by the black curvy line. And the shape is a sort of an apple shape with an empty core. Actually, the core is a magnetic coil down the middle of wire. And the shape is such that the magnetic field direction is about 45 degrees angle to the horizontal at the outside of the apple. So if we play a picture of what the plasma really looks like, whoops.
Click on it. You have to click on the picture. Move the mouse around.
Where's it going? Where it goes? What is that on the picture?
Just leave it where it is. Don't click twice or it's going to go to the next slide. Say don't click
There it
twice.
goes. It started. Okay, there it goes. So you see that picture of the plasma light emission. It's doing a real NSTX plasma shot. The shape is sort of a side view of this apple. The time is going very slowly in this movie. This movie really only takes about 1/10 of a second or 2/10 of a second. It's spread out because you're taking frames, 1,000 frames a second instead of 30 frames a second. It's 30 times smaller than normal. What you can see is light from the plasma. Doesn't look like this one quick.
You shouldn't have to click twice. Move the pointer around until you can see it.
I see it.
Don't.
Yeah. And what I'm trying to focus you on is this region here that looks like it's blinking on and off, where gas is coming out of a hole in the wall at the far side of the plasma. And you see these kind of lines, things that look like random strings or lines or filaments that are fluctuating from frame to frame. And eventually this is the end of the plasma, it sort of screws up at the end. But those lines are sort of a picture of turbulence from the side. That is the turbulent structure. It's very long shapes along the direction of that magnetic field at the outside where the light is emitted, and short perpendicular to that field, which is normal for turbulence in magnetic plasmas. Play once more. Yeah, he's trying to help. He's kind of screwed. Yeah, so you see when the gas comes out, the plasma lights up and you can see these filaments more clearly from the side anyway. Okay, so now I'm going to go a close-up, or first I'm going to tell you, zoom out. Now I'm going to tell you about what causes plasma turbulence. Well, it's very simple. It's caused by pressure changes. And there's a pressure variation in the plasma anywhere. It can make instabilities. And this is like boiling water. When it's hot in the bottom at the pot and cooler at the top, it makes bubbles. And the bubbles rise from the hot part to the cool part. Or in a sunny day in the desert, the air heated by the ground rises and it makes convection zones. You can see the air come up sometimes. So the turbulence is caused by differences in temperature in the plasma. It's hotter in the center and cooler towards the edge. And this makes what's called drift waves in plasmas. It's well-known plasma instability. These are textbook pictures of the instability. It ought to have a very long filamentary structure, as you see in the pictures. It's not surprising. Along the field line, things can move very quickly. Across the field line, plasma doesn't move. That's the whole point of the magnetic confinement. So the field line comes around and bites its own tail and keeps the plasma in along the field. But perpendicular to the field, these sort of ripples. It's kind of also like, very much like if you take a heavy fluid and you put it on top of a light fluid in gravity. It sort of makes waves and instabilities. You see this toy, you turn upside down, the oil makes fingers, and the fingers fall down. This is like fingers of plasma. The dense part being inside with the hot part, and the less dense part near the edge. So it makes strong instabilities. And that's basically the explanation. Now we're going to take a close-up view. This is the interesting part. When you try to look at this turbulence, the interesting directions are perpendicular to the magnetic field. So if you're trying to look into this filament from the side and looking up, so that's this picture. We have a view with a special window looking up along the magnetic field direction at the outside, at the edge plasma where the light is emitted. Trying to look into these filaments and see how they move in radius. And, there's a special gas buffer out here that puts a cloud of gas there, just like the cloud you saw before. And we can see the cloud emitting light, and we can see the bright part of the cloud is where the plasma is dense, because the dense plasma makes more light when it hits the neutral gas, and the less dense plasma makes less light. And this is a picture of one frame of the movie where it's a color scale. It's actually not real color, but it's a brightness scale, where white is the brightest, black is the darkest, red and green and blue are scales of brightness of the light. And the scale basically corresponds to density fluctuations or temperature fluctuations of this plasma. So what we're trying to see is the structure, shape, and movement of the plasma filaments from end on view. And this is one frame of that picture. The scale here is 5 centimeters, is this little orange bar, and this is the outside wall. So we're again looking along, just near the outside wall. So this is the outside wall to the right. Inside of the core plasma is to the left, and up and down is up and down. Oh, now I'll play the movie. This is the movie made with the Princeton Scientific Instruments camera, which is a special camera. Yeah, there it goes. All right, so this is a simple type of plasma, no heating. You can see how these things move. You begin to see them. Each one of these little clips is 28 frames, taken at 100,000 frames a second. And you can only do one of these little clips per shot. And each of these little clips is from a different shot. There are 5 on those shots. And then the next sequence here is download. Means what happens when you put on heating, and the confinement actually gets worse. That's not good. You can see that this pretty much has the same shape. Now a lot of these little blobs or structures seem to be moving outward. It's not surprising, because that's where the plasma is going. It's leaving the hot part and going to the wall, and that's what we're trying to understand, is that process of how it leaks out like that. And it's probably due to these little filaments, turbulent fluctuations that are carrying plasma out, like bubbles, you might say, hot bubbles out of the plasma. And this is the good confinement region, where the plasma is somehow better. We don't exactly know what causes it. But you can see it's quieter. And here it has a little wave and throws out a blob, but it seems to be quieter in these good confinement regions, good confinement plasmas. Not surprising. In fact, it's encouraging, because then you can try to understand why based on these instabilities. You can see that sometimes it throws off a little filament. We don't understand why it does that, but sometimes it throws off a little blob and it hits the wall. Yeah, you can go back. Alright, so that was the movie. Now, do we understand this? That's the question physicists like to ask themselves. And the answer is partly. Now, the way we understand this is with equations. And if you zoom in on the thing, you can see some of these equations. These are equations describing the plasma magnetic field, temperature, density, electric fields, velocities, all the kind of things that can fluctuate and change in the plasma are described by these equations, which are complicated looking in many parts of them, but they all boil down to just simple mechanics and electrodynamics, which is well known from classical physics, basic Newton force law, forces on charged particles due to the electric fields and the magnetic fields, and the self-consistent evolution of the fields through Maxwell's equations. Now, these are pretty well understood equations, and when you put them in for this particular case, try to model this particular situation of the edge plasma, this is what you get. You get an instability, as I said, the instability of the plasma, and it can be modeled by computer code. And this is a picture of what the output of the computer code is. Left is the high density region, right is the low density region, so it forms these kind of blobs naturally, and these waves, but in a complicated way. This is not a simple instability, it's called a nonlinear instability, and it has coupling of many different types, sizes of structures, and of course this is a picture of what happens in microseconds. Spatial scale is about the same as the plasma, but the time scale is again very fast. Similar to the time scale of the 100,000 frame a second movie. So the point is we can get pretty close to reproducing the pictures that we saw in the NSTX, the pictures of the turbulence movements from these relatively simple equations, given the temperatures, average temperatures and densities you expect in these kind of plasmas. So it's kind of a check of whether we understand it, whether the theorists can solve these equations and reproduce or produce turbulence that looks like what we see. Now, it's not completely there. Sometimes we see something different in the experiment than the theory. Here's an example of what we aim for. It's quantitative comparisons of experiment and theory. That is, graphing on the same set of axes the experimental results and the theoretical results, and if they overlay, or if they look the same, then we know we're close to understanding something, or at least we could be. It may be a coincidence that it's a good explanation, but it's a good sign. So on the left is the vertical axis is the size scale, where the biggest size at the bottom and the smallest size at the top, and the horizontal axis in the experiment is the radius of the plasma, the distance from the center. And the wall is over here, and another projection of the wall is here, and it's called the separatrix is here. The point is, the bright red parts are where there's a lot of power in fluctuations, and the blue parts are where there's little power. So this is a power spectrum versus radius of the experiment, and this is the same kind of plot based on the theory I just showed you. And the good news is that it's pretty close. These are exactly the same axes. There's no kind of fudging of the theory. The theorists weren't told what the experimental results were. They were just told the kind of plasmas it was. So it's close, within a factor of 2 or so of the average size scale. Not perfect, but close. And so that's a good sign. So we're in a process of trying to make better measurements, make better computer simulations, and see if we can find a point where they agree. That is, the experiment is explained satisfactorily by the computer simulation. And here's the last view graph, the picture that we want to leave you with, which is connection between the measurements, the theory, and the simulation. Now, I talked about the measurements. The measurements are made with this particular instrument, with this particular diagnostic, which Makeda and I developed. Measurements are made are good, but they're not the whole story. You can make many other types of measurements of turbulence. So collectively, the measurements are one kind of information. The theory, the basic theory, the equations I showed you, are another type of information about the plasma. And the connection is hard to make just from the basic equations because the equations can't be solved analytically, can't be solved in a simple way. You have to put them on the computer, which means simulations, computer simulations. And those simulations are more like numerical experiments than real theories. So they have different characters. So we have three different ways of understanding the plasma: experiment, theory, and simulation. And at this point, it seems we need all three of them to agree, to have confidence we know what we're doing. And this picture shows you schematically that they so far agree at a little bit of an area. That is, we have some understanding of what we see, but not complete. So the idea is that we're going to try to merge these circles together, align them, so that we understand what we see so far in a really solid way. And this has to be based on many different types of measurements and many different types of simulations, and understanding the simulations with theory. Once we do that, the final step is to use that computer code to predict what would be the best magnetic fusion reactor. And so far we've been doing this just sort of trial and error. And after a while it gets expensive because the machines get big. And it takes a long time to make new ones. So we're going to try this different route in addition to the normal empirical route of finding the optimum magnetic field configuration for a fusion reactor by simulations. And then of course we have to build one and test it and check that the simulations are still right. And that could lead us on the road to eventually an economical fusion reactor. Okay, that's all. Now David's going to... Don't shut it off. You can come over here.
I didn't shut it off.
Huh?
I didn't shut it off.
Okay. Okay, now that's enough of that. My throat is hoarse already. So now Dave's gonna show you what the computer can do.
Let's see.
Huh? Well, go show me your webpage.
You zoomed in?
No, I'm zoomed out for the moment, but when you find the webpage, well... Huh? Oh, we have it at the end. Really? Alright, so this is Dave's webpage. And you could tell us what's going on there.
So this is a
Speak into the microphone.
This is a web page I made over the past couple months. And I put desktop pictures from the computer on it,
Mm-hmm.
and some other stuff that I made from the computer. And it's got a few different sections.
How do you make a desktop?
So I have a program called Photoshop,
Mm-hmm.
and I take some pictures or just start from scratch and design stuff in the program
Mm-hmm.
and make pictures out of it.
Show us one.
Alright, this is one of a Mustang. It's still loading.
You had a special visitor.
Yeah.
Unplanned. What? We still got a lot of time in the course.
I don't think it's safe.
When you think of something, well, we have this special guest presentation. Oh, Veronica,
What?
you coming down here?
I was gonna change. What?
Come here.
You not to sing.
What?
You told me not to sing.
We're gonna come here.
You're gonna do what?
We're gonna make a tape eventually.
What?
You. You want it for your website? You can make a tape.
I don't wanna take that. What are you doing?
We're gonna send it to the FBI. They're gonna keep track of everybody. You have anything to say? in your defense? You deny everything?
I deny everything.
That's not typical. Where did you go today?
What is that? I went shopping.
Oh, you went shopping? What kind of shopping?
Clothes.
Clothes shopping.
What are you doing? This is so fun.
Alright, you get back over there. Let's see, say something else. I'll answer questions about the computer. Go up, show me another desktop. You didn't finish explaining how you make a desktop. What is a desktop anyway? I think Joe doesn't understand that.
It's the background for the computer. This is the one I use right now. That I didn't make, but it's just a picture that you put in the back.
Okay. What else you got on your website? Oh, show us the Mustang again. Have you ever, here's another one.
This is just a simple one. I found a picture on the internet, and I put text in it, and I put an outline around it.
Mm-hmm. Okay.
And got some just abstract ones. This.
Oh, that's nice.
And I also have other parts like cursors for the computer. I'm going to put some more stuff on it later.
Can you play, remember you took some movies of the vacation?
So I'm going to play some movies
Yeah,
that we
you
took
still got 10 minutes. Go, sorry.
in Paris, if I can find it. Are you zoomed in on the screen?
Yeah.
Hold on.
Tell us how you made these movies.
On my digital camera, which is right here, has a little movie mode on it.
You have to go further or get it in the screen. Yeah,
And
good.
You can,
That's a nice camera.
yeah, you can take videos with it.
Uh-huh.
It's camcorder.
Okay, let's see one of those videos.
Got a lot of pictures on here, so it's hard to find the right one. There's one. I gotta open it. It's still opening.
All right, what else are you going to do for your summer vacation?
I might go to computer camp
Uh-huh.
in Boston.
Right.
Maybe Dad goes to Boston again for, what is it? MIT?
Yeah, right.
But I'm not sure yet.
You may have to sign up soon.
Yeah. Hold on.
What's the hang-up here?
It's trying to get it to open. I'll have it open, but this computer's slow.
How slow?
Very, very slow.
How many hertz is it?
It's got 600. New ones have 4,000, 3,000. I'm trying to find a good time so I can open it. There you go. Alright, put this on.
Look at the sound. Where is this?
This is in I think it's in Paris.
Oh, I've got to zoom in.
Geneva, Switzerland. It just said that.
Play it again. You must have... I don't think it can be heard.
It's up all the way.
Anyway, this is a movie that the little digital camera made. Do you have any other ones?
Yeah, I have a few other ones.
Play a couple others.
Alright.
We got less than 5 minutes left.
Let's see.
Great, we've got Veronica back. Well, she's back in her natural habitat. Let's see you play Snood. What's for dinner?
Garlic.
Oh, here's a picture of a parade that we saw in Paris.
Oh yeah, let's see that.
In Paris.
No, it wasn't in Paris.
In somewhere. Geneva.
That's long. How long does it last?
30 seconds.
We'll try to find a couple others.
What are you doing? You're making a video. What are you doing? Oh, it's a video.
It's security
Put it
purposes.
on your, put it on the computer.
Yeah, we can put this on the computer.
Oh,
That one's no good.
on the phone.
Hmm?
On the video.
You don't.
Yeah, we do.
You can't put that in.
Yeah, we can.
Okay.
Make a QuickTime movie out of it.
Okay.
And so,
Oh.
I did it. Somebody did it for me. Well, you have to go to the Computer Resource Center at the lab, and people already know how to
Can't
do
do
it.
it at home. Oh, I'm having trouble finding one.
One more. Well, just give us some pictures then. Give us some mountain pictures.
Yeah,
2.5 more minutes.
Do you get pictures of the pictures of the computer?
What are you doing?
Where's the computer? Untitled.
here's a picture of the Geneva Fountain. I don't know if you got one of those.
Oh, is that just a picture, or is that the movie?
It's a picture.
That's a pretty big fountain.
Yeah, it's huge. And see if I can get some pictures of the mountains. Got some piano accompaniment. Are we out of time then?
No, got another minute.
Alright, let's see. Here's a picture of the mountain. Switching
Alright.
train that we were taking up the mountain.
Oh, wow. That's nice.
And one more.
One more.
Here's another picture of a different mountain.
Oh, what are those mountains?
I don't know. What is that?
I think that's the where the Eiger was. 29:10. We got 50 seconds according to the.
I think that's enough. It's hard to say.
Let's let it run out by itself. Show us another picture.
Alright. What do you want to put this time?
Anything you want.
Yeah, picture.
Oh, we didn't take a picture of the cat. Let's get a picture of the cat first.
Alright.
We can do something.
Cat.
Boom boom. I'll step on him. That would wake him up.
Don't step on the cat. Don't step on the cat.
I'm trying to roll him over. There.
Boom boom. Boom boom. Hey boom boom. Hey boom boom. Did you get fat? He got fat.
No.
No. He didn't get fat. He looks fat. He's a cute cat. He's looking at the camera. Don't step on the cat. I think we're done. I think it's not even recording anymore.
Alright, stop.